Hello, this is Alan Katz. I want to thank everyone for the opportunity to do this talk. And I'm going to be talking about the advancement and linearization of wideband power amplifiers.
Hey, Alan. Hey, this
yes.
is Mike.
Yeah,
if you don't mind, let me do a few announcements to start off here.
Oh, okay. Excuse me.
That's all right. Hello, and welcome to Advances in Linearization of Wideband GaN Power Amplifiers with Dr. Alan Katz. I'm Mike Hamilton, your host for this IEEE Microwave Theory and Technique Society webcast, which is sponsored by National Instruments. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We'll send all registrants an email when the archived webinar goes up so you can revisit it or share it with your colleagues. Second, we encourage questions. We'll answer them after the talk, but you can submit them at any time during the discussion. Enter them in the Q&A box on the left side of the webcast window, and please don't forget to click Submit. Third, some words about the interface. You can enlarge slides by clicking on the green rectangle at the top right of each slide area. If you're listening over your computer speakers, you can adjust the volume in the media player area at the upper left of your screen. Remember, you may also need to adjust your system's master volume. The icons at the bottom of the webinar window include a file folder. This links to a resource page from where you should be able to download PDF copies of the slides. Now let's introduce our speaker. Dr. Alan Katz is a professor of electrical and computer engineering at the College of New Jersey. He's founder and president of Linearizer Technology Incorporated, which now includes Linear Photonics LLC and Linear Space Technology LLC. He received his doctorate and baccalaureate degrees in electrical engineering from New Jersey Institute of Technology and a master's degree in electrical engineering from Rutgers University. Professor Katz holds 17 patents and has written more than 100 technical publications. He received the IEEE Microwave Society's MTTS Application Award in 2015 for his work in linearization, the IEEE Microwave Magazine Best Paper Award in 2010, the William Randolph Lovelace II Award for Outstanding Contributions to Space Science and Technology from the American Astronautical Society in 2002, and he was the recipient of the IEEE Region 1 Technology Innovation Award in 2007. He also served as an MTTS Distinguished Microwave Lecturer. Dr. Katz is a Fellow of the IEEE and has served the MTTS in a number of capacities. He is chair of the APED and MTT chapter in the IEEE Princeton Central New Jersey section, and he's also the Technical Program Committee co-chair for IMS 2018 in Philadelphia. In addition, he has contributed to organization of the Sarnoff Symposia and BINMOS meetings and has organized the Trenton Computer Festival for a number of years in Princeton and Central New Jersey. So now it's my pleasure to turn the virtual podium over to Alan Katz for Advances in Linearization of Wideband GaN Power Amplifiers. All right, Alan. All yours.
Thank you, Mike. It's really a pleasure to talk about a topic I'm very excited about and involved with. And let me outline, because we don't have a lot of time here and I have a lot to cover. I'm going to briefly review the area of GaN HPAs, go over basic linearization so we're all on board in the same place, discuss ways of achieving wideband performance, because this talk is focused on wideband applications, and then I'll discuss some of the limitations in trades, get into the issue of when you talk about wide bandwidth, when you go over an octave, some important points. I'll talk about multi-octave linearization, and I'll spend a little time on memory effects and instantaneous bandwidth. And finally, I'll show you some examples of performance with wideband amplifiers and conclude the webinar. So when we look at wideband amplifiers, I have a couple examples of I've taken out of the literature and presented. The first one shows an amplifier that will go from 100 megahertz to above 2 gigahertz. And, oops, I don't know if I have a problem here. All of a sudden, things have changed. on my screen. So this amplifier gives more than 100 watts of power, and it gives very nice efficiency. When you go higher in frequency and look at wideband amplifiers, high power is still a little bit of a challenge. I show a chip or an amplifier here that was discussed by a previous webinar presenter, Jim Komiak, that covers the range from 2 to 20 gigahertz. And so the example here is 10 watts. People are really pushing the power level for GaN amplifiers. At the recent IMS International Microwave Symposium, there were amplifiers up in the millimeter wave range up to almost 100 gigahertz, producing power of more than 50 watts. So things have are really changing very rapidly in terms of what can be done with wideband amplifiers made in GaN. Now, this talk is focused on linearization. And the question is, why do we need linearization? Well, if you're in the communications industry, the interest has been in getting more information through a limited bandwidth. In fact, all we hear is, how do you make the pipe bigger? And if you look at the relationship between information rate, we see it's dependent on bandwidth, but it's also dependent on signal-to-noise ratio. And signal-to-noise ratio is often limited by the distortion in an amplifier. That becomes a limitation. So if you want to get more information rate, what you need is a higher linear amplifier. The way we traditionally get higher linearity is to take a power amplifier and reduce its output power. We operate the amplifier at its maximum power level or saturation. It is highly distorted because it's limiting the output. But as we back the amplifier off, as illustrated, the amplifier becomes more linear. What we do with linearization is correct for some of the softness in the transfer curve of the amplifier and allow the amplifier to operate closer to saturation for a given level of linearity. If we take this to the limit and look at what is the best we can do in an amplifier, we come up with an ideal characteristic that is shown on the screen. In this type of situation, we want to have a constant gain as close as we can to saturation, but we can't just think about gain. When you talk about nonlinearity in an amplifier, you also have to think about the phase shift in the amplifier. It may not be obvious, but when you drive an amplifier with increasing power level, the phase shift or delay through the amplifier changes. And both of these components contribute to distortion. So when we linearize, what we want to do is correct any change in phase or any change in gain to produce this characteristic. Of course, once we get to saturation, then there's nothing we can do because the amplifier can't produce more output power than it's capable of producing. But we can improve the characteristics of the amplifier up to the point of saturation. This sets a limit on what we actually can achieve with a power amplifier. It also introduces or makes us aware of why people talk about peak to average power ratio and why it's important. Because if you have signals that are going into the amplifier, but these signals change in level, when they go above the saturated power of the amplifier, its maximum power level, they get clipped off and they cause a lot of distortion. So, and we can't do anything about that. So the peak to average power ratio gives us a metric or a measure of where we can operate an amplifier in terms of the signals going into the amplifier. And this may be clearer in the next slide. What I've done here is taken two extremes in terms of signals that you might test an amplifier with, and they represent real signals that would go into the amplifier. One of the common metrics for measuring distortion amplifier is what's called two-tone carrier intermodulation ratio, and that is the blue curve to the left-hand side. If we look at this type of test signal, it has a peak-to-average power ratio of 3 dB. This means that if we back an amplifier off more than 3 dB, we can actually correct the amplifier to a very, very high carrier intermodulation ratio. But if we operate the amplifier at less than 3 dB output back off, and I can show you that in the following, here it comes, slide here. Let's say we talk about a 30 dB C to I carrier intermodulation ratio. You can see that if we were operating the amplifier at about 3.5 dB output back off, and let me just make clear, I use the term output power back off, but what that means is that we're referencing the output power of the amplifier to its saturated power. So when I talk about a back off of 1 dB, I mean that the amplifier is being operated at 1 dB less output power than its saturated power level. This gives us a way of comparing different amplifiers, amplifiers that have different power levels, but to get an understanding of how well they're operating with respect to saturation. An important point to make is that when you make an evaluation in terms of output power back off, that you always reference the saturated power to single carrier saturation. It turns out that when you use modulated signals or multi-carrier signals, that the saturated power of the amplifier may be less than when you have a single carrier. So to make your comparisons, compare apples to apples, you always want to compare the output power, no matter what you have going into the amplifier, to the power when the amplifier is driven with a single carrier. If we look at the slide, and you see the red O there, this corresponds to somewhat maybe about 3.25 dB output power ratio. In a two-tone case, the amount of improvement we could get by linearization, in any form of linearization, is when we hit the blue curve. So in this particular case, we might get about 3/4 of a dB in improvement by linearizing. Now, if we had a higher peak-to-average ratio signal, and that's illustrated by the red curve that is to the right, this represents a many carrier signal. It's actually a metric called noise power ratio, which stands for many tones. It represents what happens when you put many signals through an amplifier, and it actually is produced by taking noise and filtering the noise, putting a notch in the center of the noise and looking at it. The important point here is that this represents a high peak-to-average ratio. In fact, one of the highest peak-to-average ratio signals you might put into an amplifier. So this gives you the opposite end of the bound. And you can see if you wanted the same 30 dB, you'd have to operate the amplifier at 6 dB output back off or higher to achieve a 30 dB carrier to intermodulation ratio with this type of high peak-to-average ratio signal. In normal signal traffic, you're probably going to be someplace between the blue and the red curve. So if we look at this and we appreciate what we're seeing here, this gets us to the first rule, and that is you can't linearize an amplifier that's already linear. If you already have a linear amplifier, you can't get beyond the blue or the red curve here. And if you're a designer, this means that when you design the amplifier, if you intend to use linearization, you don't want to optimize the linearity, what you want to do is optimize the efficiency and saturated power of the amplifier, because then you can use the linearizer to improve the linearity. Now, we look at what factors you need to consider when you decide, should I linearize or not? Well, in engineering, the first consideration, which seems to overshadow all of them, are economic considerations. If you're going to linearize, it's got to make economic sense. And if we look under this, what affects that economics, we see that the more nonlinear an amplifier device is, the greater the advantage is going to be to linearize. This fits right with the concept that if you have an amplifier that's linear, you can't do anything, so you're not going to get any advantage. We look at GaN amplifiers compared to the more traditional microwave amplifiers made of gas. One of the things that have focused on linearization for GaN has been the fact that they tend to be more nonlinear than gas, so you can gain more by linearizing a GaN amplifier. If we look at what can you achieve for GaN HPAs, high power amplifiers, you're probably looking at something like 3 to 6 dB of more power in linearization. Now, this depends on the frequency, the nonlinearity, a lot of factors, but this is typical of what you can see. When you improve the back-off power of the amplifier, so you can operate closer to saturation, amplifiers are more efficient the closer they operate to saturation. So for this type of increase in power level, you're also going to see a significant increase in amplifier efficiency, typically doubling the efficiency of the amplifier. And at the same time, since you can operate a smaller amplifier, use a smaller amplifier to produce the same power level, you're going to produce a size and weight reduction by linearizing. Now, other factors that affect the decision to linearize are thermal load. You have a problem always when you're designing an amplifier of controlling the heat. And if you can operate the amplifier at lower power, you can produce a lower thermal load. I've seen people linearize just for thermal consideration. Another factor that may not be obvious, but when you think about it, when you look at the size of an amplifier, the bigger the size of the amplifier, the more economical it is to linearize. So if you had a 10 kW amplifier and we look at the costs of adding linearization, it's almost in the noise. It's not an important factor. On the other hand, a 1 watt amplifier, it may be very hard to justify linearization, because the linearization technique is going to be the same cost no matter what type of what is the power level of the amplifier. And in the same way of thinking, if you go to higher frequencies where power is more costly, it may make sense to linearize a smaller amplifier. At 100 gigahertz, it may make a lot of sense to linearize a 1 watt amplifier, while at a gigahertz, it may not. We look at different forms of linearization. There are 3 standard forms of linearization, but when we look at what is practical for linearizing power amplifiers, pre-distortion is the major used form of linearization. I don't have time to go through all the details here, except to say that this is what's being used today, and it really doesn't make sense to use feedback or feed-forward linearization for what we have today. And what I have illustrated here is the concept behind I'm trying to illustrate here how predistortion works. And what we do in predistortion is, as we drive an amplifier harder, its gain drops off or falls off. And what we do is we put a box or some sort of device in front of the power amplifier elements that generates a function that goes the opposite way. So when the amplifier compresses by a dB, the predistorter will expand by a dB, and when you put the two together, what we will get is a amplifier that has constant gain. Now, at the same time as we correct gain, we also need to correct phase, because, as I mentioned, as you drive an amplifier harder, we also change in phase. So the predistorter must correct both gain and phase, and we start looking at wideband applications. We need to correct that gain and phase with respect to frequency, so that many amplifiers, in fact almost all amplifiers, do not have the same nonlinear characteristics with respect to frequency. So when we look at the predistorter, we got to think not in terms of a set of curves, but we have to think in a set of surfaces so that we match the nonlinear characteristics over frequency. And this has to be done both in gain and phase. And when we get to really wideband applications, we must make sure that we equalize the amplifier also so that our curves match up with the amplifier. If we look at predistortion linearization, there are two forms of predistortion linearization: digital linearization and analog linearization. Digital predistortion linearization tends to be the dominant form today. It is the dominant form because of its widespread use in personal communications, cell telephone, Wi-Fi, those applications. It is very nice because what you do is you generate your corrective function by programming in what we can think of as a lookup table or a function that generates the corrective characteristic. This means that you've got a lot of independence in the nonlinear characteristics of the amplifier, since you can correct them by programming. And it also is very nice if the modulator, the digital modulator, is integrated with the amplifier, because you can actually correct in the modulator for the distortion of the amplifier. This means that you get the linearization hardware basically free at no cost. However, there is an issue, and that deals with bandwidth. The modulator must have sufficient bandwidth for the linearization. If you have a signal of a certain bandwidth, you normally, when you linearize, want to correct for distortion that is adjacent to the modulated frequency in the adjacent bands. So at a minimum, you have to generate energy in the two adjacent bands. This means that you need 3 times the basic modulated signal bandwidth as a minimum to correct for adjacent channel distortion. And the situation actually gets worse than that, because you need to generate higher order terms and just the third order terms in the adjacent channel. So if you want to get the best correction, you can't just correct over 3 times the bandwidth. You have to go to a wider bandwidth to get the better correction, to make the curve more correct. Many DSP type linearization people recommend a bandwidth of 5 times the signal bandwidth. If you want to get even better performance, you may go to 7 times the bandwidth. Now, this means that your modulator has got to process at a much higher bandwidth than the signal, and this can be a problem to generate the digital processing. Another problem with DSP-based linearization is when you want to send multiple signals through an amplifier, because if the signals are already digitized, you've got to undigitize them and redigitize them to combine them. You cannot have a linearizer for each signal. That doesn't work because you're trying to linearize the peak signal when all the signals combine together. So this becomes a difficulty. Another aspect or difficulty with digital linearization is that you cannot easily adjust the nonlinear characteristic with respect to frequency. The correction circuitry looks at the input signal level, and it really can be blind to frequency. There are ways of handling this, but it means that you complicate the digital processing. The way this is usually gotten around is to use adaptive linearization, where the system compares the input and the output, and depending on where the signal is in the band, it optimizes the correction characteristics for that energy distribution. If we look at digital versus analog pre-distortion now, there's no question if the modulator has sufficient bandwidth, it's a no-brainer. It makes sense to go and use digital modulation. This is why it's quite popular. But when we look at wideband applications, analog pre-distortion really starts to have some advantages, because as the bandwidth increases, analog becomes more cost-effective, because in some cases it's even impossible to make the digital processing fast enough to handle the required bandwidth. A rough rule of thumb I use is 25 megahertz. And what I say is that this is not the deciding frequency, but if you're going to deal with signals that are greater than 25 megahertz in bandwidth, you should consider using analog linearization. You should make the comparison to see how the two compare and which one gives you the best benefits. As you start to go up to multi-gigahertz bandwidths, because of the limitations and cost of digital processing, really you find that analog becomes your only option. Well, the question is, of course, can you make analog linearizers over very, very wide bandwidths? And the next slide here shows you an example of a pre-distorter that goes from 50 megahertz to 2 gigahertz in bandwidth, and that shows useful operation over more than a 2 to 20 gigahertz range. Now, let me explain what you're seeing in the figure. You have two sets of curves, an upper set and a lower set. The upper set represents gain, and the lower curve is your small signal gain of your pre-distorter element. When you drive the amplifier harder, you want the gain of the pre-distorter to increase. And what you see in the lower upper curve is the small signal gain. As you drive the amplifier harder, that curve moves up in gain, so that when you get to large signal levels, you have an increase, in this case here, across this full band almost, of 3 dB, which is typically what you need for many solid-state amplifiers to correct them. You also have to be able to generate the same type of wideband function in terms of phase, and that's the lower curve. Here, what we're concerned about is not the absolute phase, but the delta in phase. That's what's important. And what you see is between large signal and small signal, you notice the phase is going down as you drive the amplifier harder. This is typical what you need for a GaN and gas type amplifiers. You need the phase to be reduced as you drive the amplifier harder, and as you go higher in frequency, you need a larger change in phase with frequency, and this shows you with this particular sample pre-distorter you can produce this type of characteristics. I note that what you need to think here of is this in terms of a surface. I mentioned earlier, rather than just in terms of curves. So at each frequency, with respect to frequency, you have a changing characteristic that becomes a surface, or two surfaces, one for gain and one for phase. one of the things that you can do to make the process of linearization easier is rather than build one linearizer, you can build multiple linearizers, one from each band, and then you can combine these, multiplex them or switch them together. And this shows you, the next slide here shows you some examples of available multi-band linearizers where the linearizer has a single input and output, but it can be set up to operate over multiple bands where each band is optimized for that frequency range. So one solution to the wideband application, if it's allowable, is to use a multi-band linearizers in a single box. And I've seen up to 4 linearizers in a single container being produced and available. The other end of this is to do linearization is one linearizer that operates over a very wide band. The next slide illustrates that you can get the type of linearizer characteristics from analog circuitry, not just at the general microwave frequencies, but up into the millimeter wave frequencies. Again, you see the small signal and large signal characteristics and the change in gain with power level here produced by this demonstration box. And this illustrates that you can produce linearizer characteristics over a very wide bandwidth. We've produced analog linearization successfully up to 100 gigahertz. Now, one of the limitations when you deal with wideband linearization is the problem of ripple. You design the right characteristics, the surfaces you need to correct for the gain and phase, but when you connect two components, the linearizer and the amplifier together, there is always some sort of impedance mismatch with respect to frequency, and this produces ripple. The slide I'm showing you here is used to illustrate that given the amount of ripple you have, there's a limitation in the improvement you can get. In the example that is pointed out there, let's say you have a 2 dB peak-to-peak or plus or minus 2 dB ripple. If you have that and you're operating the linearizer where you have a C to I improvement of 30 dB, this means that at some points in the band you'll have 30 dB, but at some points you also will have a degradation that could be as much as 3 dB. So you drop from 30 dB to 27 dB C to I. And of course, the worse the ripple is, the worse the degradation in the carrier to intermodulation ratio you're going to have due to the ripple effect. The next slide illustrates the problem of instantaneous frequency. If you have multiple linearizers, you can only operate energy in a given linearizer at a given time. However, many applications we want the signal not to be at one frequency and then later at another frequency. We want the signal to be spread instantaneously across the full band. This can be from a single carrier that's modulated with a very, very high data rate, or it can be the fact that we want to send multiple signals across the band at the same time. So in these applications, we have to have a system that responds instantaneously very, very rapidly, because the envelope of the signal is going to change extremely rapidly. This is what I refer to as instantaneous bandwidth versus static bandwidth, where you have a narrow band signal and it can be operated at different points in the band, and the linearization amplifier process works fine. So the question is, with analog linearization, when the same thing applies for digital, if you could get the bandwidth, can you respond rapidly enough to follow this rapidly changing signal? And what I illustrate here is an example with two NPR signals that have been spread apart by more than 2 gigahertz. And you see that you can maintain your NPR, both the high end of the band and the low end of the band, despite the fact that the signal is changing very, very rapidly, instantaneously. We've illustrated or produced linearizers with more than 8 gigahertz of instantaneous bandwidth. I don't know what the upper limit is, but I do know you can certainly have instantaneous signal spreads close to 10 gigahertz and be able to follow those with an analog, a properly designed analog linearizer. Another factor that we hear talked about is memory effects. Memory effects are changes in an HPA's nonlinearity due to the past history of the input signal. In other words, the output is not just a function of the input, but is also a function of time. And there are a number of sources of memory effects. I'm just going to touch upon them here because they can become important. One of the biggest ones is what's called frequency memory effects. And this is just another way of saying that the nonlinearity of the amplifier changes depending on the frequency of the signal that is entering the amplifier. And of course, the solution to frequency memory effects is to produce a predistortion circuitry whose nonlinear characteristics change with respect to frequency. Another important effect in solid-state amplifiers is the fact that when you drive changing a high peak to average signal through an amplifier, you get changes in the current that the amplifier draws, basically in the drain and gate bias circuitry. And one of the nice things about GaN amplifiers is that because of the higher voltage that GaN operates on, the amplifier draws a smaller amount of current for a given output power level. And this means that the problem of decoupling or dropping the change in voltage, bias voltage on the amplifier is somewhat less of a problem with GaN, but it still is something that you must consider and be aware of, and is not easily corrected by standard linearization. You also have in GaN devices memory effects, changes that are device related. These are typically referred to as traps and things like that, where you get charge stored in the device and the charge doesn't leave the device immediately. And GaN historically has had problems with device-related memory effects, and they're not easy to solve. It's really a device-related problem that you must be aware of when you're working with GaN devices. There is also thermal memory effects, and this is a result of the fact that as the device heats up, its gain and in some cases its phase characteristics can change with heating, and the heating remains. It is a memory, remembers where the amplifier was before. Generally, this is a low-frequency effect, but there are some devices that can be sensitive to heating at fairly high frequencies and that you need to worry about. This brings us on to the issue in wideband amplifiers of multiple octave linearization. And that is where you have a signal that is more than twice the frequency. Normal linearization assumes that the signal is less than an octave wide, and it is only affected by odd order distortion. You don't have to worry about even order distortion products. But as soon as you become or deal with a frequency that's wider than an octave, then you get even order products that enter in band and that you need to correct for. And these are both harmonics, such as the second harmonics, but even worse than that, the biggest components you get are the sum and difference components, F1 minus F2 or F2 plus F1, depending on the bandwidth you're dealing with. And these cannot be corrected by odd order distortion. You have to correct them using even order distortion. And the way you get around this, or one of the approaches to getting around this problem, is to use a push-pull circuitry, 180-degree combining of your components. If you combine, for instance, your amplifier components in a push-pull circuitry, this will suppress your even-order harmonics. If you're dealing with linearizers, the linearizers themselves may generate even-order harmonics. So to put the linearizer or nonlinear distortion elements in a push-pull circuitry allows you to get rid of the even-order distortion products. This next curve shows you the type of suppression. You can get around 25 dB or more suppression by using push-pull type of balanced 180-degree balanced circuitry. However, even when you used balanced circuitry, you may not get adequate suppression of your even order components. Then you can go through a circuit like this that introduces pre-distortion of the even order components and the odd order components both. The next slide shows you a mimic linearizer that uses all these concepts that was produced a few years ago. This has 180-degree combiners. It has push-pull linearizer elements. And if you look at the results of this mimic, this shows you the performance over a 6 to 16 gigahertz band. And what you see again here, if we look at the curves, one of the things we're trying to do is we're trying to make that gain constant, the red curve at the top at 6 gigahertz. And that is the linearized transfer characteristic with the mimic linearizer in place. The blue curve is the original. And you can see what we've done is we've pushed the 1 dB compression point much, much closer to saturation. And if we do the same thing at 10 gigahertz and the linearizer does at 16 gigahertz, we've moved that 1 dB compression point 6 dB closer to saturation across the full band. At the same time, we have to also correct phase. This chip does pretty well. At the low end of the band, you can see that we didn't have that much phase change to start with, but the linearizer reduces that phase change. Again, at 10 gigahertz and also at 16 gigahertz, we get a big improvement of this. Basically, using the linearizer, we reduce the distortion from the phase change from greater than 30 degrees to under 10 degrees. And we look at the results in terms of a metric like C to I. When we do this, we improve the carrier intermodulation ratio or the spectral regrowth or whatever we have in the amplifier by correcting the distortion products. And this will work across the full range for this very wideband amplifier. So in terms of the trades, here, when we look at this and we look at the differences between doing wideband linearization and narrowband linearization, what we get here is it allows us to operate over a large, continuous, and unrestricted band. This is using a single pre-distortion linearizer. It allows us to use wideband modulations and spectral spreading across the full band. We can correct for in-band harmonics and both even and odd order distortion products. And an interesting factor is if, as you correct the even order distortion products, you also you also can improve the efficiency of the amplifier because you can use harmonic cancellation at the lower part of the band. However, there are negatives. It's more difficult to align. You've got to get these surfaces right to match across the full band. You require equalizing both the gain and the phase delay over very wide bandwidths, and you have the limitation we discussed that you need to get rid of your gain ripple because that'll set a certain amount of degradation depending on the ripple you get. So, in conclusion, I know I've shown you here that the ability to linearize GaN HPAs over very wide bandwidths, 10 gigahertz or more, has been illustrated. And the ability to produce linearizers with desired nonlinearizer characteristics, both even and odd, over a continuous multi-octave bandwidth. We've shown that you can get improvement of both IMD and harmonic distortion. That you'll get greater improvement in your various nonlinear metrics can be achieved by using multiple bands rather than a single band package. What I'm saying is it's always easier, and as the last bullet says, in general, the narrower the bandwidth, the higher the improvement that you can get by linearizing. But even when you do things over very wide bandwidths, you can get substantial improvement over these very wide bandwidths. Thank you.
Wonderful. Thank you very much, Alan. Okay, so now it's time for our question and answer session. And so before we start, just remember that you can still submit questions through the Q&A panel. All right, so we have a number of questions here, and we'll try to get through as many as we can. Let's start off one from, it looks like it's referring to a slide earlier in your talk. And the question is, why is the saturated output power with the modulated signal lower than the tone-based?
The reason this is, and there's two ways you can look at it. One reason is that when you put multiple signals in, you're going to produce distortion products. Those distortion products subtract from the power level. When we talk about power level, we mean the signal power level, not distortion power level. So that if you put a couple of carriers into an amplifier, you accept the carriers as useful signal power, but the distortion products are not. So they would subtract from the power level in the signal. So, for instance, you had about 10 dB C to I ratio, which is kind of typical at saturation. About 10% of your power would be in distortion power, so you'd be down about a dB. There's another factor that enters into this, and that is some amplifiers also decrease in power. They don't remain constant as when you go beyond saturation. And so that also can reduce your power because you're spending a certain amount of time while the signal is being transmitted above saturation, where the actual output power of the amplifier goes down rather than up, and that gets subtracted from the total power.
Okay, excellent. Here's a question specifically about GaN. What is the effect of GaN on heat dissipation and thermal noise, presumably with regards to linearization?
Well, there's two issues here. One of the problems with GaN is that you produce more power in a smaller space, because if you compare a GaN and a gas device, for example, in the same space that you might produce a 10-watt gas device, you're producing 100 watts of power that must be dissipated by the GaN device. Now, GaN generally has better thermal characteristics, can be operated reliably at a higher power level than gas, but there are limitations on that. And what it means is you got to take your thermal energy out of the GaN amplifier more efficiently than the gas because you have less area to basically suck the heat out. And there have been a lot of interesting techniques available that have been generated. Part of the differences that our people are working at is the substrate of the GaN devices. You hear about GaN devices that use silicon carbide, that use silicon. There are people developing GaN devices that use GaN as the substrate. I meant to say diamond as a substrate because of its very excellent thermal properties. But there are ways to generate means of getting the heat out of GaN. I'd be happy to talk about some of those offline.
Okay, that sounds fair enough. So here's a question regarding Doherty GaN PA. So can you comment on analog linearization of Doherty GaN PA over 20% bandwidth? Are there common issues? Comments on level of difficulty, etc.
Yeah, and with regard, I left out completely talking about Doherty and some of the other techniques that are available that allow an amplifier to have high efficiency at back-off, okay? All these, or what I said, applies to these amplifiers. Doherty, you can talk about envelope tracking amplifiers that allow the amplifier to have higher efficiency when the amplifier is operated at a backed-off level than a more traditional amplifier. All of these produce higher nonlinearity. So if you take a Doherty amplifier, and this doesn't have to do with bandwidth, though it certainly is an issue, but the Doherty amplifier has to be linearized, so it has higher efficiency. Let's say it's operated at 6 or 8 dB output back-off. It has greater efficiency than a traditional amplifier does, but it must be linearized because it's more nonlinear at that back-off point than, let's say, a traditional amplifier that's been backed off 6 or 8 dB, and thus you must design a linearizer for those characteristics. I do not know the answer. People are developing techniques, load modulation techniques, that allow Doherty amplifiers to give better bandwidth, but I have not seen data, I haven't done it myself, looked at how the nonlinearity of a Doherty amplifier changes over these wider bandwidths, percentage bandwidths. So that's what you need to look at. You got to see how the nonlinearity changes, and then see how you would design the surface, the gain versus frequency versus power level surface to match that characteristic. And I don't have the answer to that question as to what happens in the wider band Doherty amplifiers to their nonlinearity. Need to look at it.
Yeah, sounds like an interesting topic.
Yes.
Okay. How about a question for lower frequency things? How cost effective are these linearizers at VHF frequencies, for example, compared to using higher powered devices that are backed off?
Well, again, this goes back to the trades between digital and analog linearization. At low frequencies, depending on the bandwidth you have, you may not be going very high in frequency, and the capabilities of digital linearization may be available to you. So if you're in VHF, the first thing I would look at is how wide a band we're talking about at VHF. And the best approach may be to digitally linearize inside the modulator, if you can get a hold of the modulator, or build a digital linearization circuitry. When you deal with narrower bandwidths, you also can start to look at other techniques besides pre-distortion. If you're dealing with signals that are below 10 megahertz and really preferably less than 1 megahertz in bandwidth, feedback linearization is worth looking at. It is a viable means of linearization. The problem with feedback linearization is that it can't really be made to work well above a few megahertz. It becomes very difficult to apply, and this is independent of the operating frequency. So it's a bandwidth question.
Okay, I think there's this may be more of a two-part question. So one part is, why is gas more linear than GaN? And the other is, I think maybe could be answered in the same statement. How do GaN memory effects affect linearity compared to gas?
Well, let me take the why is GaN more nonlinear than gas. I really don't. I'm not a device physics person, so I don't know the absolute answer to that. I know it is, however, and as gas, as you go higher in frequency, gas tends to become more non-linear. We see the same effect in GaN devices. We also saw that as gas matured, that gas became more linear. And there's a possibility that as GaN matures, the device technology will be such that it will become more linear also. And then that is where your trade comes up. Do you linearize or do you not linearize? Do you make the amplifier bigger, or do you linearize and allow you to use less devices and less power to get to the same output power point? Now, the second part of the question asked about the effect of memory, I believe was, right? Memory effects and trapping, right?
Yes.
In GaN versus gas. And the answer is, to my knowledge, there's no real difference between the two, except that GaN devices, possibly because of the newer technology, the devices, they have had more problems with trap effects. They're more pronounced than in gas. And as the device technology becomes better, we're certainly seeing that there are less problems with these trapping effects.
Okay, I think we've got time for maybe one more question here. At what power level does linearization for GaN amplifiers at, say, the 2 to 6 gigahertz frequency range typically make sense?
Can you repeat that, Issa? At what power level?
That's right. At what power level does linearization for GaN make sense in the 2 to 6 gigahertz frequency range?
Well, that is hard to give an exact answer to it, because it depends on how much linearity you need also on that. Obviously, the higher the linearity you need, the lower the power level it would make sense to linearize. But I would start to say looking at linearization at a linear power level of around 10 watts is where I would, and that's kind of off the cuff there. I don't have an exact number, but I would say when you're looking at 10 watts or more, I'd certainly look at the trades and look at what the costs are and my factors. There are reasons why you might want to linearize at a lower power level, not just in terms of absolute cost, but in applications where efficiency, for instance, power consumption is important. People are using linearization in handsets because not just because of cost factors, but because of you don't want to deplete your battery supply. So there are applications like that which affect your decision. But about 10 watts would be my starting point to at least start to look.
Sounds reasonable. Okay, so ladies and gentlemen, I'm afraid we are out of time. We do still have a number of questions in the queue, and I believe the presenter will follow up on these unanswered questions offline. As we said earlier, the session will be archived on the Society website at mtt.org, and all registrants will get an email reminder with a website address when it's available. For attendees that would like to receive PDH credits, please follow the link in the webcast view and use the code provided on the last slide of this presentation. Once again, I'd like to thank Dr. Katz for an excellent presentation. Our thanks also go out to National Instruments, who is the sponsor for this webinar. And special thanks to our audience for joining us today. We hope you found today's event valuable and that you'll return for future IEEE Microwave Theory and Techniques Society webcasts. Thank you and have a good day.